Hello everyone, welcome to lecture 16 of the course on quantum entanglement and non-local games. I am Dhiraj and today we are going to look at the perfect embezzlement strategy in C algebra model. So what we have seen so far is that for this embezzlement game, we saw that in order to achieve a fidelity of 1 minus epsilon with epsilon approaching 0, what we need is that the dimensionality approaches infinity, right? And as we moved ahead, we then we saw that okay, in order to define an entanglement in infinite dimension, we needed the notion of the C algebra, which we had defined, and then later we defined the notion of states, measurements, and reversible operations on those sort of state spaces. And now it's time to go back to that embezzlement game and see how in this C algebra formalism we can achieve the perfect embezzlement, right? So over there what our goal is that in case of embezzlement is that okay, we have a state AB which is shared by Alice and Bob, and then there is some catalyst sort of a state psi, and we need to use this catalyst to transform our original state to EPR state on AB, and the catalyst state psi remains as it is. So we saw that in tensor product of Hilbert spaces, we can't find such a catalyst state psi, right? And the idea here is that what if we can choose, idea is to choose the state psi AB as an infinite number of zeros and an infinite number of EPRs. And what I do is that I sandwich my state 0 0 in between these, right? So I have the psi AB and then I sandwich my state 0 0, and now what I do is that I need to basically, in order to transform the 0 0 to EPR, what I do is that I apply a left shift operation. So left shift operation, and this left shift operation will transform it to 0 0 tensored infinity, and then I have EPR, and then I have EPR tensored infinity. So what I do is that okay, at position 0 I have my own state, at position 1 to infinity I have these EPRs, and at positions minus infinity to minus 1 I had these zeros. And now what I did was that I applied a left shift. So basically from minus infinity to minus 1 I had all these zeros, so this 0 got absorbed in the other zeros, and at position 0 I got this EPR, and then I have the remaining EPRs. So the thing is that if I have an infinite number of zeros and I have an infinite number of EPRs, I can apply a left shift and transform 0 to EPR. But idea here is that okay, we need the notion of, so the thing is that we need to express these infinite number of EPR pairs in terms of an abstract state. Right. And what we found precisely was that okay, this is actually not possible in order to express it in tensor product of two Hilbert spaces. However, what we can do is that we can consider this as a state into CAR algebra registers. So consider this as a state on to CAR algebra registers. So how do we do that? So in order to do that, what I have is that I have the state S5 plus from A tensored min A to C, which is given by S5 plus on XA ZB tensored XA prime ZB prime. So this essentially equals, so this phi plus is my EPR. Okay, these are infinite number of EPRs, and these are essentially product of J from 1 to infinity phi plus XA J ZB J tensored XA prime J ZB prime J, and then phi plus. So each of the sort of operators on each of these qubits are sandwiched between these phi pluses, right? And what I'll obtain as the end outcome is the product of J from 1 to infinity delta AJ AJ prime delta BJ BJ prime. Right. So here delta is the Kronecker delta function. So why is it so? Because see, if AJ and AJ prime, so basically if both are 0 or both are 1, then essentially I get a sort of a 1 over there. But if you know, if any of these qubits I have, you know, just a single x or a single z or a single xz, then essentially the expectation value of phi plus on that is going to be 0, so that you can check. So essentially we'll get a 1 only when each of these AJ and AJ primes are equal and each of these BJs and BJ primes are equal. And similarly we can also express 0 0 tensored infinity as an abstract state. So to do that, we define an abstract state. S0 0 from A tensored min A to C, that corresponds to an infinite tensor product of 0 0 states. Now S0 0 on XA ZB XA prime ZB prime is then product of J from 1 to infinity 0 0 XA ZB tensored XA prime ZB prime 0 0, right? So actually we index these from minus infinity to 1, minus infinity to minus 1, right? So we have EPRs from 1 to infinity and 0 0s from minus infinity to minus 1. So minus 1 to minus infinity, and this equals product of J from minus 1 to minus infinity 1 minus AJ 1 minus AJ prime, right? So you again check that Z's will not contribute anything to this sandwich product, only the X's will contribute, right? And the thing is that both of these aj's and aj prime, they must be equal to 0 in order for this expectation to be 1, otherwise the expectation will go off to 0. Now we define our embezzlement strategy. So we choose the resource entanglement state. As catalyst to be S00 tensored S5 plus such that S catalyst on XAZB tensored XA prime ZB prime equals product of j from -1 to -infinity 1 minus aj 1 minus aj prime times product of j from 1 to infinity delta aj prime delta bj prime, right? And overall the thing is that overall we have an initial state 0 0 and we have a final state phi plus, right? So this is the state at position 0. So at qubit index 1 to infinity we have EPRs, at qubits index -infinity to -1 we have zeros, and then at position 0 we need to make this sort of transformation. So overall my initial state is as follows, that S initial, it acts on XA ZB tensored XA prime ZB prime is nothing but product from j from 0 to -infinity now. So the thing is that initially I have a 0, so in position 0 also, so basically so instead of this entire product, so what I have is that this j starts from 0 to -infinity, right? Because at position 0 also I have ket 0 0. So I have product of j from 0 to infinity 1 minus aj 1 minus aj prime times product of j from 1 to infinity delta aj prime delta bj prime. Okay, and my final state is of the form of product of j from 0 to infinity delta aj prime delta bj prime times product of j from -1 to -infinity. Okay, or let me write down this before. So finally what I want is that at position -infinity to -1 I have ket zeros, and then from position 0 onwards I have EPRs. So what I have is delta aj prime delta bj prime, right? So which can be accomplished by making a left shift. Accomplished by Alice and Bob making a bilateral shift, bilateral left shift on their qubit. So basically both of them have performed their corresponding shifts, and so basically this allows us to achieve an embezzlement with epsilon equals to 0, which leads to a quantum input game with probability 1. So quantum input game win with probability 1, right? Basically because if epsilon is 0, then you win the game with probability 1 minus order root epsilon, which is 1, right? So this finally finishes the notion of perfect embezzlement, and we saw that okay, indeed we need an infinite number of qubits in order to win the game. So yeah, that's it, and I think we have covered quite a lot in this course. So maybe it's time to take a pause, or maybe complete the course for now, but we might come back sometime soon. If in case you have any feedback for me, let me know. Thank you. Hope you enjoyed this course for now.